My name is Kevin Hale. I'm one of the co-founders of Infinity Box Inc. Our company is based here in Tampa, and we run a product called Bluefield. It's an online HTML form builder, contact forms, online surveys, event registration, simple online payment forms. We do it. It's pretty nice. If you want to know more about stuff that we do like this, you can read some of our writings at particletree.com. So, again, this is 5 user interface laws every software designer should know. A lot of these laws that I'll mention, I think a good number of you will probably already know them, but I think a lot of people don't go into sort of the mathematical structures and the history of the experiments that sort of created them. And then you find out when you go through all that, and you learn a lot of things about the assumptions that were made and how to better apply them to our software. I also try to do my best to give you some tips on how to actually apply the math to your environment. So, first law, this is Fitt's law. So the guy's name is actually, everyone's always wondering like how do you spell this law? The guy's name is Fitz with an S, so it's Fitz's law. So, basically what this demonstrates is that the bigger the object, the easier it is to point at it. How the math actually works is the average time to get to the object is a function of sort of the distance to the object and sort of the width of the object. Now what's really interesting about this, and if you want to sort of break down the formula, is this: A here and B here are functions that are numbers or constants that are determined when you do the experiment out. And so what this is sort of is the reaction time, the start and stop time, not too important here. And the B is the slope, or the speed at which the person is reacting to the thing. This part is the most interesting part of this law. It states that the interaction between sort of the speed here and the and sort of whatever objects and the size differences, the relationship is in a log format. So that means if you have something that is tiny and you make it a little bit bigger, right, that makes a huge difference. But if you have something that is already big and you make it bigger, that does not make such a huge difference because it's already big. For example, if I have like a thumbtack, right, and if I make it as big as a bread box, it's like it's easy to point at the bread box, right? It's so much easier than the thumbtack. But if I have a house, right, and I'd say, oh, let's make it like a 2-story or an apartment complex, both of those things are very easy to point to. So if you have buttons on an interface, right, and they're very tiny, making them a little bit bigger makes a big difference to the user. If they're already gigantic and huge, making it twice as big doesn't make it twice as easy. The other thing that's sort of interesting about Fitt's law is that how the experiments were actually done. This experiment only shows things in 2 dimensions. So the guy that came up with it, Fitz, he was an aircraft designer, aircraft controls. He was a pilot, actually. And so the way he made the experiment was he had 2 metal plates, and then there's sort of this like metal pen thing that he held onto to one side of the plate, and it said get to the other side of the plate. And he would time how long it would take you, and the plate could go this far off, so you can overshoot it. And he would time like how fast it would take you to stop at the other metal plate. It's how the experiment was done. So that means there's a lot of assumptions that are taking place. One assumption is that it's only in straight lines. A lot of people like to think that they try to use Fitt's law in terms of like lots of weird curves or different kinds of paths. So let's do eraser. So let's say we have 2 different objects, right? And we have this. So we have this rectangular object here, and we have this square object here, right? And I have a cursor sitting over here. The way you have to do the calculation is straight lines from the center point of each of these objects. So you have is anywhere from here to here is good. Right? And so it turns out that the square is easier to get to because let's say I started off with this smaller square and I was like, oh, I'm going to make it bigger. It's going to be easier to point to. So you're like, and this one made it like a bigger square. You find out that this is not any easier to point to from this position on the cursor. Happens a lot of times in menus. I see a lot of people like, I'll make this menu bigger, and they'll just make it longer, and that does make it easier to point to. If, let's say it's on the left side and your cursor is always here on the right, it's still hard to point to if it's super narrow. Second thing that's interesting about Fitt's law, in terms of human-computer interaction, is when we have a monitor, like so, have this really interesting thing called edges, right? Where the cursor can no longer go beyond the point of the edge of the monitors. So we have these edges here, and then we also have these points. And technically what ends up happening is because the cursor just stops, that top point, these widths are considered infinite widths, and these corners are infinite widths in dimensions, right? So in terms of software design, the point up here at the very top, this whole edge, is easier to point to than any other object you'll have on the screen, even large objects. And this point in the corners are extremely easy for you to point to because you just throw your cursor really quickly over to the side. The other thing that's interesting is that most browser software, however, doesn't get to take advantage of that stuff because it's like right here in the center, right? So you don't get advantages of fits lot and sort of menu items that go all the way to that or into the corner. Early designs of, I think, Windows 2000 and such, they actually had windows where the top very pixel there, that one pixel, actually couldn't be clicked on to select. So the menu items, if you jammed it all the way up to the top, when we click, OS X at all times used to be able, you can do that. So it made those menus really easy. Eventually, in further versions of Windows, they changed that. But when you're thinking about menu design, especially on like interface terminals at like museums and stuff, this stuff is really, really interesting. The edges and the corners where you can do really interesting stuff. And it's also why like expose and such are really interesting user interface sort of interactions. I think some of the more relevant points is like Chrome has some edges and points because Chrome has no left side sort of borders on there. So you can do interesting things sometimes. I've not seen any websites do this, but since there have one left side that has no sort of Chrome little parts on there, you can actually use that edge side and use this principle to create sort of easier access to something. Oh, so velocity. So later on, a study was done to sort of dissect, like, well, what is it? What is the component of sort of drawing this straight line or pointing at something that sort of makes things fast or slow? And they found out was that every line or every sort of action that people take to draw a line is composed of two parts. So you have this like one phase here and this like second phase here. Right? And this was called the high initial velocity. It said regardless of how big or how far this thing is, this initial speed velocity is always the same for whatever the person is doing. Right? It's very, very confident. People are like, how long have you get started? And then as they get closer here, depending on the size and distance, this is what eats up all the time in terms of pointing at the object. So it's like, and you're like, okay, I gotta calculate, slow down, all right, let me get it, and stop here at this point. So it turns out there's some interesting things in terms of this only counts to linear motions in time, this formula. So it doesn't take into account like hardware acceleration, which actually it turns out mouse hardware acceleration makes things harder to like point at smaller objects, right? And things that some people have been starting to do is sort of magnetizing different points and sort of interfaces. So when you get close to them, it automatically sort of auto selects them or helps you do stuff. All the things that you can do is sort of make target points start to get bigger as you get closer to it. Therefore, it helps that phase. Fitz's law, super awesome. Second law. So this is Hicks law. So Hicks law is about cognitive processing time. And the way it was sort of set up, the experiment was Hicks created all these little lamps. He made between 2 and 10 lamps. And he would say, I'm going to light one, and you tell me which lamp it was. Right? And what he found out was the more lamps there were, the longer it took them to sort of process and tell them what the light was. Again, what we noticed here that's really interesting about this mathematical formula is that it's done in a log 2. Now, instead of doing big things or big numbers changes creates long processing time, this actually has to do with how we do sort of large number selection of processes with a short-term memory. And so what we actually do, it turns out, is we subdivide, right? So if there's 4 lamps and we have to choose one, what we actually do in our brains is go, okay, from which group, so this half is, and let's say this is glowing, this half is glowing, and then you choose between these two and then you divide here. So the brain sort of does this too, right? So the subdivide in sort of a binary manner, how many binary decisions you make in order to figure out which is a selected item. Now, a lot of people like to use Hicks's law and says, okay, so as long as I keep the number of things minimized in a selection sort of process, then they'll be able to process it a lot faster. Not quite. So this has to do with sort of every object is sort of the same. You're seeing which object needs to be pointed at. In menu design, and a lot of people like to use Hicks's law for menu design, and it's really sort of inappropriate because a lot of people, the menu goes like this, home, about, news, your mom, contact, right? And the problem is, if I tell you to select something, and you've never seen this list before, well, you actually still have to read all the items before you get to the things. You go, okay, if I say, pick your mom, you're like, okay, your mom. So, what that causes is that the reaction time actually goes in a linear fashion because of that. The only time that it helps you is, let's say, like an address book. Because if you put things in alphabetical order, people can then use subdividing to figure out, okay, what letters I want to use, and then subdivide into it, and that sort of helps. So, Hicks's law, less items, easier to figure out which is the thing that they need. Oh, one of the cool things about Hicks's law is that they actually found out. So let's say these are bits. So a number of pieces of information that you process. This is reaction time, these are the number of items. They found out, so this is what it takes, right? For the average person, they actually found a correlation with IQ. So if you have a lower IQ, it takes longer. Higher IQ, a little bit faster. Obvious, but they have graph for it. So this is called the steering wall. Now, what's really kind of cool about the steering wall, it's also known as the Kant design law, is that it wasn't done with experiments. They didn't do experiments first. The several people who derived this law actually figured it out using mathematics alone, and it's heavily derived from Hicks's law. And when they did experiments to sort of see how accurate it was, they were really surprised at how well it works in all these different kinds of situations. And what it describes is, if you have a two-dimensional tunnel or path, how well someone can get from one point to the end point, right? So I have a tunnel like this, right? How long it takes to get from here and get to there, right? And it describes actually two things. It takes how long it will take, right? And then also the speed at which you will go at that object. And what they found out was the relationship is strongly derived from the width of the tunnel. The wider the path, the faster you go. Think about it, kind of like on a highway. The wider those lanes are, the faster, or the easier it is for you to go faster down that path. Now, this is sort of the fancy pants version of this equation. And what it does is it allows you to account for curves, right? So it's like, again, we have the start and stop time. We have this sort of speed here. These are constants that are derived when you're doing the experiment, but it's a function of the curve. And we have sort of the length of the tunnel up here, and we have the width of the tunnel up here. And so if you've got like curves that like will spread out and go in and out, you figure out sort of, all the complicated math for that. If you only have straight tunnels or straight paths, you can just use a formula like that, which makes it much easier to understand the relationships. Basically, the wider it gets, the faster they go. The longer the length is, the slower it takes, or the lower the reaction time. So what are sort of the implications of this? Well, in menu design, all right, so we have a lot of like pull-down menus. So you'll click up at the top menu, and then it'll have a bunch of different options, and you'll select this option, and then this will pull out another menu, and then there's all these different options, and you want to get to this one right here, right? Well, that's a path, right? You click here, if you click here, follow this path, then drag it down, get onto this. This will tell you how long and how fast it will take to get there. What's interesting is, lots of people, again, always think about paths in terms of how wide, and they think, oh, this makes it easy to do. But the thinner this path or tunnel is, because this is sort of the limiting reagent, this is sort of the thing that will cause the limitation of how fast you can go through this. If this is really, really thin, it's what makes it a lot harder to get to the path. So depending how many turns, indeed. One thing that's interesting about this function is it actually doesn't take into account multiple turns or forks in the road into a maze or a path. And so what you do is you sort of combine steering law with a little bit of Hicks law, and you can get something a little bit more accurate. But it says basically you want to limit the number of turns or how many trees levels deep, and you also want to make sure all your paths are nice and wide. So this isn't really a formula. This is Miller's law, and actually there's two different kinds of Miller's law. One is a Miller's law in regards to information theory. This is not it. This was a psychologist, and he wrote a paper talking about in the human mind, you can this is like sort of the number of objects you can hold in working memory very, very quickly, and it's about 7 plus or minus 2, depending on the person and circumstances, but it's usually about 7. And what he found out, that's really, really interesting about this, is that we don't think in terms of bits, right? We think of things in terms of chunks, right? So, for example, like if I asked you, give me a number between 0, give me a digit, a single digit, right? That is about 3.3 bits, right? Because there's like 10 different digits, 0 through 9. And because of that, you'd have to select from all those pieces of information. But if I actually, take a letter from me between A through whatever the 10th letter is in the alphabet.
J.
Wow.
That came from the keyboard guy, by the way.
So A through J, he had a theory that basically, since the alphabet actually has something like 10 bits, because there's like 26 little letters you have to choose from, then you have to dissect all that would take even longer. But it turns out it's not, right? You're able to think in terms of chunks of whatever the immediate thing that you're thinking about. So whatever your selected choices are, regardless of all the, so like, choosing between 5 different words that you have on a screen, it turns out like you have no problems just choosing from the 5 words, not having to start from the entire dictionary and then work your way down. Now, what's really cool about this is like, why is this limit there, right? This is stuff is like, if you're choosing between, let's say I give you 7 tones, and then you have to do something very specific depending on the tone that I give you. So basically, an input could have a possible 7, and the output has a possible 7. But that's about at the point where your brain can handle it without making mistakes a large amount of time. And they were trying to figure out after a while, like, what causes that? It's like, why is that limitation? Why is it at 7? And what they found out was that it's highly related to the phonological loop in the memory system. Right? So it's like, you can hold in your brain very, very quickly 2 seconds of audio information, right? And it's tied to language, right? And it turns out, in 2 seconds of sound, you can do about 7 digits, or 6 letters, or 5 words on average. And that's related very, very closely with sort of how many things that people could accurately spit back out depending on what you sort of give them in terms of input. Now, what's really, really interesting about that is they found out that, so how fast we can say the numbers 0 through 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, in 2 seconds is what really determines sort of that limiting factor. In China, it is much faster to be able to say all the numbers. So they can actually hold 9 plus or minus 2. So I guess the practical thing is if you're creating menu items and you're in China, they can handle more options all at once. Also might explain why they love to see things more complicated. So this is the power law of practice. And the easy way to say this is basically, it's a description of learning curve, right? Like literally, like practice improves performance. The more you do something, the better it gets. But we have a formula, and when it turns out it's in a power curve. Actually, there's a dispute over like which curve is more accurate. So this is a power curve. Some say it should be called an exponential curve. But the reason is this was aggregated over time. So they had several people do it. And then they aggregated those numbers and they figured out the curve for the aggregate all the time trials that they did of the practice. And it turns out if you just look at individuals, it tends to be about more exponential in terms of the fitting curve, but it doesn't really matter. Basically, if you do one practice, you get better exponentially or in powers better. And then when you do the second practice, it's not as much. The third practice, not even a little bit less. But as you practice, it takes lots of practice to get significantly better. add the object. But you only have to get someone to do something at least 1 or 2 times, and they're significantly way more sufficient than they would be if they haven't done anything again. So basically, in interface design, one of the greatest things you can do if you have something that is complicated is get someone to go through something at least once, or have them watch something at least once, right? And that way you have them not starting at a blank slate, and having them go through the maximum amount of time it takes for them to possibly do the activity. And what's really cool about the parallel practice is it works in all kinds of situations. So whether you're doing immediate response tasks, perceptual tasks, like motor perceptual tasks, recall tasks, text editing, high-level deliberate tasks, like in game playing, practice always follows the somewhat same exponential curve for every individual. So those are the 5 laws: Hill's law, Hicks law, Stirring law, Miller's law, and the power law of practice. Learn those, find them to your interface, and go have some fun. Thank you guys.